For this optimization, we can use, for example, gradient descent. It's a very common optimization algorithm and all its variants in optimization, but also there are other optimization algorithms. So for the gradient descent, we start with an error function delta, even here. So this is the output k minus the desired k. And for example, one always positive error function is its square. So this is also called the loss function. And in this particular choice, this is the mean squared error. So to this error function, we can now apply the gradient descent. It is also called a stochastic gradient descent in our case of neural network training. So we have this that x new is equal to x old minus alpha times the gradient of x old. In our case, now it will become at the w new, so the weights will be the w old minus alpha times the gradient of the error k depending on x and w old. So for the gradient nabla, we need to compute the derivative to each weight w of y of the weight vector w. So in our case, we can apply the chain rule, so that the outer derivative times the inner derivative, and after these manipulations here, we get these equations. This delta and the derivative with respect to the weights. Then we have this delta k, and here we have the derivative with the respect to the weights, and here's the output. And we can compute this inner derivative first for the output weights, and again we will use the chain rule, and finally we will get this equation 4 here. So we have these equations 2, 3, and 4. So if we now plug this result 4 into equation 3 and equation 2, we obtain the update rule for the gradient descent for the output weights. So what we're doing is we're applying the chain rule to calculate derivatives, and then we will have this update rule. That is the weight oj new is equal to the weight oj old minus alpha times delta k vectors x and w, and the derivative of this s of ok times h of j. So this update rule is telling us that the update is equal alpha times output delta times output derivative times its input hj from the hidden nodes. We observe that they only have local processing for the update, which makes it suitable for massively parallel processing, for example using a GPU or a graphics processing unit. For the hidden weights, the inner derivative of equation 3 becomes a bit more complicated. So we have here the derivative with respect of the weights, output k. Then we have all these manipulations here, and we apply the chain rule, and we will finally get this equation here. And again, now we plug this result for the hidden weights 5 into equations 3 and 2, and we obtain the update rule for the gradient descent for the hidden weights. And we have this equation 6, which tells us that the update is equal alpha times the backpropagated delta times derivative of hidden function times its input x, y. So we've seen we have all these quite complicated ways to calculate to get the update rules for our output weights and also for our the weights for the hidden units. But once we pass this, we can apply. In the libraries, they have an automated way of calculating gradients and calculating this, what is called the backpropagation. So this algorithm is also called the backpropagation, and we need to do this update for each output node k. This is in principle the same rule as for the output nodes, just with its corresponding input and output. So this means that the backpropagation is just a consequence of applying the gradient descent algorithm to neural networks. And a popular alternative to the gradient descent, or let's say a refinement of gradient descent in neural networks, it is the algorithm that's called ADAM. And once again, we can look at the Keras documentation and you see that we have this available algorithm, so the stochastic gradient descent, RMS prop, ADAM, ADAGRAD, and those are very popular algorithms, optimizers. So hence, for all nodes, we retain a local processing. So we just look at one node, call its input x of y, its output O, its weights w of y, and its desired output d. Then we obtain its output with this sum here. So sum of the weights times the inputs, and then the output is a function applied to this sum. So if it is an output node, the difference delta to the desired output d is given by O minus d. If it is a hidden node, we use the backpropagated delta from an output difference delta O, weight to the output node WO, and sum for the output node SO. And we have this. Then we get the local weight update given by this formula here. And this we can see in this diagram. So we have inputs, we have weights, we have the sum. In this sum, we apply a function into the sum. In this case, for example, the sigmoid. So the sigmoid is applied to the sum, and then we have the output. So the weight update during training with the output difference delta.